Hello everyone, welcome to the third and final part of File I/O in Python. In this video, I'll finally be covering the actual I/O operations. These operations allow us to create new files or open existing ones, and then either read data from the file or write data to it. Opening a file for reading or writing is pretty simple on its own. At its core, the function used for opening a file simply requires a string specifying the path to the file. The actual reading or writing of the file can be anywhere from super simple to very complex. It all depends on the data involved and how it needs to be processed. In some cases, you will have to write the code to handle the reading and writing operations yourself. In other cases, there are Python modules out there that will handle all that for you. Some examples of these modules include those that handle formats often used for configurations, like JSON, YAML, or even XML. Which brings us to the first use case for File I/O, configuration files. Sometimes the programs we build will require a lot of settings to perform their jobs, settings that can potentially be changed based on certain situations. We can store them in certain formats like the ones mentioned earlier and use their respective modules to load them up. Another use case is reading in target files to process the raw information inside them. A good example of this is reading in log files and looking for key information so that it can be printed out in a friendlier format for you to understand. Which brings us to the third use case, writing information generated by our programs. It's nice that we can print things on the screen to look at as the program runs. However, if the program runs for a long time and generates a lot of information, it would benefit us a lot more if the data was stored in a file. That way we don't have to try to read the info as it flies across the screen and eventually get lost in the command line buffer when too much information is generated. This is particularly important for programs that generate logs. Alright, now let's get into some actual coding and go through some examples. The first example is a pretty basic one. So the function we use to open up files for reading or writing is simply open, and we don't have to import anything to use it. It's immediately available to us. The first argument for the open function is the path to the file. And then the second argument specifies the mode in which we open this file up for. So it could be for reading, it could be writing, it could be specifying that we want it in binary mode versus text mode. We can also specify that it's creation, in which case it'll create a brand new file, but if that file already exists, then it'll just raise an error. We can also open up for appending and writing, which means that basically it will just append whatever we write to it at the very end of the file and not overwrite what already exists in there. And we can even open up for both reading and writing. So we're not limited to just doing one or the other. So in this example right here, we have the open function, and we're using it to open up a file called out.txt. We haven't specified a full path or anything, so this is relative, which means that it's going to open up a file out.txt in the same location as this Python file. And we're specifying that we are opening up this file for writing. Then we store the resulting file object, which in this case is a text IO wrapper, into a variable called fout. And from there, we can call the functions that belong to this object to write the information into the object, which will end up sending it to the file. So we got two write functions here, write and write lines. Write, we pass in a single string, and it'll write that string. And as you can see, I've got a new line at the end of the string. That's because write does not automatically append a new line to the end of the information we wrote to the file. It's not like print, which would automatically append a new line to whatever we printed on the screen. Write lines allows us to pass in a list of lines to write to the file. And as you can see here, these lines also have new lines because it still does not automatically append a new line to these lines that it writes to the file. And then finally, we call the close command to close up the object in the file that we are writing to. It will save the file. It's important to make sure you do this, otherwise it could cause issues. So when I run this example, we're going to open up a file called out.txt, and it's going to print out these lines here, the first line, the second line, third line, fourth line. It should all be on new lines. So real quick, I'm going to show you the directory that I'm working in. So we got a bunch of Python files as well as Jupyter Notebook files from the previous videos, as well as a CSV file, which I'll get into that later. But we don't have any out.txt files. That's just to show you that we don't have that file yet. So then I'm going to run our example, which is file io1.py, hit enter. We don't get anything on the screen because I don't have any print statements or anything like that. And then if I check the directory again, we now have an out.txt file. And I'll open that out.txt file, and there's the lines that our Python file wrote to the file. In the second example, I'm going to demonstrate how to read from a file. I'm going to open up the file that I generated from the previous example and then read in the information. And then we're going to manipulate that information and write it to a second file. In this example, I'm also going to demonstrate the two modules that we covered in the last two videos, OS and Pathlib. Now, OS is just a module containing functions that return paths as strings. It doesn't have anything really special to it. So it's essentially the same as just passing in a string into the open function. But it's still good to, demonstrate it in action, even if we're not going to do anything too crazy with it. The pathlib module, however, does provide us with an object called path to help us store our file paths and directory paths and stuff. So I am going to demonstrate how the open function can easily accept a path object as well. And we're going to basically read in the data, store it in a list called data, but not before manipulating it to change up the information so that we print out something slightly different in the new file. Basically, we're just replacing the words first, second, third, and fourth with their numeric counterparts in the lines. Now, not every line is going to have first, second, third, and fourth. It's just actively checking to see if it has it, and if it does, it will replace it. It won't throw an error if it can't find it. Each line is basically going through all these functions. It's not the most efficient, graceful way of doing it, but because it's not something that's going to throw an error or anything, we can do this without any issues. And then once we modify the line, we append it to the list data, and then after we're done, we close the file. And then down here, we're going to open up our new file, out2.txt, and we're going to write the new lines into that file. So as usual, I'm going to show you the directory. We've got all our files from before. We also got the out.txt generated from the last example, but we have nothing else. So I'm going to run the example. No output as usual because we have no print statements. We check the directory again and we have an out2.txt. It's basically almost the same as the lines in out.txt, except this time instead of spelling out the words first, second, third, and fourth, we've got the numeric version of those words. Okay, for this example, we're going to go over a subtopic to file IO. It's not directly related to file IO. It's actually related to a lot of things in Python, but file IO is definitely one of those things that tend to cause this to happen a lot. And that is exception handling in Python. I'm only going to cover enough to deal with file IO with exception handling, but I will have a video completely dedicated to exception handling to cover more on the topic. But I think it's important to be able to cover a little bit in this video because it is something that can happen a lot because you are not limited to just things happening in Python. File IO has the external factor of the system that you're working on. Like, will the files be there or will writing to the file cause an issue or something like that? But I am going to show a bit of it because it is kind of important, and I'll also show you how to handle it. Now, I apologize in advance because this demonstration might feel a bit lackluster. Unfortunately, the only exception that I really know how to trigger on the spot is the file not found exception. There are other exceptions that can happen during reading and writing of a file. I just don't know how to trigger those on purpose. But what I can do is show you how to handle exceptions properly so that you can avoid having exceptions mess up your program when you're trying to do stuff with file IO. Plus, another reason why I have to show you exceptions is that the next thing I talk about actually helps with dealing with exceptions. So the one exception I can demonstrate to you guys is the file not found exception. It's a pretty easy one to trigger. You basically have to try to open a non-existent file for an operation that does not include creating the file for you, like writing operations would typically do. So a good example is trying to open up a file for reading that doesn't exist. I should probably set the mode to read and not write, because if I set it to write, it's just going to open up a new file for writing. So we got this simple one-line code trying to open up out3.txt for reading. We don't have a file out3.txt in this directory, so when it attempts to do so, we'll get a error saying that it couldn't do it. So when I run this code, we get this trace back and an error message basically saying out3.txt does not exist. And the traceback is basically it showing you where your error occurred. It'll show out the line of code. In this case, it's actually very simple. It's just showing the one line of code where we try to call the open function to open the file. And then it says the exception name here, and then it's the exception message itself, error number 2, no such file or directory, and then it prints out the name of the file that we tried to open. So how do we handle an exception? We basically have to use a try except block. For a try except block, you start with the keyword try, a colon. This opens up a code block, so we have to indent this to go under the try code block. So we're trying to open a file for reading. Then we say except, and in some cases, you can just have a blank except, but I would not recommend it. Always specify what you are trying to catch. And we're going to catch the file not found error. Now we could also stop here if we'd like this. And this isn't too bad as opposed to a blank accept, but you can also say as a variable name. And I usually go for E. I think most people just go for E. It's simple. Then under this, we can do tons of things. We can either have it quit the program gracefully, or we can have it skip over this file and so that it can loop back around and try another file. We can also have it print out the error message either to a log file or on screen so that we still know at least that this exception occurred. So we're going to print out the exception, and that's pretty much it. We try to open the file. If an exception occurs, we catch it and we print out the message. So when I run this, we don't get a traceback anymore, but we do get the message saying, hey, this file did not exist. And technically speaking, if this was in a much bigger piece of code and this was like in the middle of some huge process, the process would likely have continued if we didn't tell it to quit out of the program when it caught this exception. In this case, the program just ends because that's all there is to it. Handling exceptions is something you're most likely going to have to do every single time you deal with files because anything can go wrong. It's an external factor. It's not something Python can directly control. Files may not exist. File might be corrupted. You may not have the right permissions. You may have coded something wrong in Python and it attempted to do something to a file that it just couldn't do, like write or read something. There's all kinds of errors that can occur. So you would always want to have try exceptions around it. You don't have to try and accept all of the exceptions, just the ones that you know are most likely going to occur with your code. And it's important because let's say you did successfully open up the file for reading or writing, and you're in the middle of doing one of those operations, but then something goes wrong and it crashes out. Or in this case, you caught the exception, but because of the exception catching, it didn't get to complete what it was doing. You now have to deal with the file object that's handling the file, because if you don't, you could potentially lose data, especially if you're writing to the file. I can't simulate that, unfortunately. That's something really hard to trigger to happen on purpose. I'm going to kind of spoof an exception thing. It won't really have the threat of loss of data, but at least I can demonstrate to you how you take the steps to handle it in the event something like that happens. So give me a second to type out the code and I'll show you how it works. All right, so here's our code. So we're now opening up a file for writing, so we're not going to worry about the file not found error. And we're also going to write some lines to that file. Then right here, I'm spoofing an exception. It's not going to be like a real exception that happens while trying to write to something or trying to read to something that would cause us to break out of this, but it will trigger the accept clause here. And when it does, it's going to print out my exception message, which I just said spoof exception. And then we've got this finally block. The finally block is something that executes no matter what. We could successfully go through the whole try block. Finally will still execute. We could hit an exception that causes the accept block to execute. We would still go through the finally block. The finally block is to make sure that no matter what, the set of code under it will always execute. And the purpose of our finally block here is to ensure that no matter what, the object will close the file that we're writing to ensure that no data has been lost. So in this finally block, we evaluate to see if the object has been closed. And if it hasn't been closed, it's going to print out this message and then it will close it. I actually don't think I can. Can I? It might grade it out. Yeah, it's going to grade out because obviously the exception is going to prevent it from ever executing, but we're going to put it there and just pretend. So it's going to try to get to this, but oh no, an exception occurs. So we'll just make it look like that. So it seems realistic. We tried to close it, but we couldn't. So make sure it definitely gets closed. So we run the code, spoof exception, it hit the exception, and then it said file reader not closed. So it made sure it got closed. So that's why it's important to know about exceptions for file IO, is that you're very likely going to have to use try exception blocks all the time when you're dealing with file reading and file writing so that you can catch the stuff so that it doesn't cause your program to crash or doesn't cause you to lose data that you tried to write to a file. And another reason I wanted to demonstrate this is because there is another keyword that I want to go over with file IO that actually works pretty well with try except blocks. It's actually supposed to be paired with try except blocks because it helps make things a little bit easier to read and code. And that keyword is with. The with keyword allows us to create a code block, and it interacts with objects that have two magic methods defined, the exit and the enter magic methods. I have not gone over these, and I will do a video more focused on the with keyword at a later time to go more in depth with them. But basically, an object must have these magic methods defined in the class so that the with keyword can interact with it. In the case of file IO, the file object is going to attempt to open up the file that we are trying to get into, whether it's for reading or writing, and then perform all the functions under the code block. Then once it reaches the end of the with code block, before it exits out of it, it closes the file that the file IO object was interacting with. And it does this without us having to call the close method ourselves. We will never have to call the close method on our own when we use the with keyword. And this actually makes try except code blocks a little bit easier to deal with because we don't have to ensure that there's a finally code block in there, making sure that that file gets closed. The with keyword will take care of it for us. So just as a quick example, I'm going to run this file and it prints out the lines from out2.txt just fine. All right, so now we're going to do this with an exception. So we're going to still open up the out2.txt file for reading, and we're going to continue to try to print out all the lines, but like before, we're going to raise a spoof exception. This is the only way for me to do this example because in order for me to show how with will handle it, I have to make sure the file actually opens. I could say, oh, hey, open up a file that doesn't exist, but then in that case, it would fail to open and therefore the variable will not be established. It's going to print up the exception and then it's going to check to see if it's closed. And if it's closed, it's going to say that the file is closed. So I'm going to run the program and there you go. It says file is closed. So that's the benefit of using the with keyword with file IO is that when you want to make sure it gets closed properly, despite whatever exception might get caught, with will do that for you. Now, last minute, I came up with a fourth example. It's a little bit more complicated, but I thought it would be cool to throw something like this together just to show off to you guys. So we're using pathlib solely for all our path stuff. And the first thing I did here was create a fpath variable to store the path of a file we're going to open up for reading. Now, you may have noticed this little magic attribute right here. So what this particular magic attribute does is it references the full path of the file that this attribute was called in. In this case, file io4.py. So we're creating a path object that stores this file path, but then we're calling the .parent function, which will return just the full path to the directory that this file is stored into. Then we are combining it with a file name pilot_db.csv. So we're basically creating a file path that's pointing to this CSV file stored in the same directory as this Python file. And for those of you who don't know what this is, a CSV file is basically a comma separated value file. It's basically a list of files line by line that are broken up into comma separated values. And this is probably the simplest form of data storage, especially for writing code to parse it, because all you have to do is split the data up by the comma. So after we have this path, we open up the path for reading and we read in the lines one by one. We get rid of the pesky new line at the end because that'll throw some data off. And then we split the elements up by the comma and store them as a tuple that we then append to the list p data. And then I print out the p data just to verify that it actually prints out. So now we create a new path, and just to make it simple and not typing all this out again, I basically just take the fpath, call the parent function again, but this time I add a different file name to it. So we're going to store our new data into a YAML file. So I open up this file for writing. I create our first YAML keyword, pilots, and then for each item in pdata, I write a YAML list object into the file. And then once it's done, it will close up and then we can look at the file. And just to show you what our CSV file looks like, we're going back to ships and piloting information again, as usual. So we got our pilot names first, their ID numbers, their type of ship, and then the name of their ship. And they're all separated by comma values. I'm going to run the Python file. It prints out our list. And then at the bottom here, we've got the pilot info YAML. I'm going to open that up. So we got a list of pilots, and each one has a name, an ID, a ship type, and a ship name, and with their correct values assigned to them. Pretty cool, right? So that's just a more complicated example that I just wanted to show off. You wouldn't code your own YAML parser by hand. There is a module out there that can do all that for you. It's called RuML YAML. It's very, very good, and I would highly recommend using that. Don't bother trying to make your own YAML parser. There's really no point when there's already a very good one out there. And that's about it for File IO in Python. There's definitely more advanced stuff you can do with this. I just wanted to make sure that you guys could understand the basics. I will probably cover some of the more advanced stuff later on down the line, but I'm still more concerned about covering the basic stuff for you guys. So I hope you've enjoyed this video and found it helpful, and if you did, then please hit the like button and leave a comment below to let me know what you think. And if you want to see more, head on over to Wayfair Coding Academy channel to check out my other content. And while you're there, subscribe to the channel to stay up to date on new stuff as it comes out. Thanks for watching, and I'll see you all next time.